cool, these microphones. I could walk around, you know, like Steve Jobs or something. But I have too many slides to take care of, so pardon me if I stand behind the podium. So I'm going to talk a little bit about how OCT works first. It's kind of ridiculous for me to say much about this because we have Jim Fujimoto coming up next, or coming up soon, and he is the master of that. So I'm just going to give you a brief introduction about OCT, and then we'll go forward. I'm going to talk about just how to apply just some knowledge from OCT to make a new classification of AMD. So with spectral domain OCT, there's a fairly broadband light source, and that light gets pumped into the instrument, and there's a beam splitter in there, and it splits half the light off into a reference arm and half into your eye, or a person's eye, and the reflection from the eye is then combined back again with the light from the reference arm. And that makes an interferogram, and curiously, the kind of ingenious part of spectral domain OCT is the depth of the reflector kind of encodes the interferogram. So near the zero delay point, which is a kind of point where the reference arm and the arm into the eye is the same length, the frequency is relatively low. And if you move that reflector back, the interferogram has a higher frequency, and if you move it back further still, has a higher frequency. So we can measure the frequency and know where in the eye the reflection came from. And you end up getting a fairly complex sort of waveform that can be decoded with a Fourier transform. It's hard to get anyone going back. Can be decoded with a Fourier transform to make an A scan, and many A scans make a B scan. Now, the ingenuity of spectral domain OCT is that there's depth encoding of the reflection, but that's also kind of one weakness in that it's harder, or the instrument is less sensitive to these higher frequency sort of interferograms. So increasing depth also means decreasing sensitivity. There's a sensitivity curve to spectral domain OCT that just is shown kind of in a schematic form like this. So near the zero delays point, you have high sensitivity, but that sensitivity falls off. Now if we look at ordinary OCT, you have the highest point of sensitivity is put in the vitreous cavity, and the lowest point is found posteriorly in the eye. So we have great sensitivity to look at the vitreous, which is fortuitous since the vitreous doesn't really reflect much light, but on the other hand, you can't see that well deeper into the tissue. If we push that zero delay point further back and use the other part of the curve, we have an ability to image deep in the choroid, and this is basically the idea behind EDI OCT, but notice that we don't get to see the vitreous. So if we want to use spectral domain, we have to pick which area we want to look at. We can look at the vitreous and retina, or we could look at the retina and the choroid, but not both simultaneously. Source OCT goes through the set spectrum of wavelengths sort of sequentially in order, and it builds up an interferogram over time. And just like the spectral domain OCT, that interferogram is decoded by a Fourier transform to get an A scan. Many A scans make a B scan. So what's different about this is that the sensitivity fall off is much different than spectral domain. Do you recall this slide, what I showed earlier? And here would be a representative slide for the sensitivity fall off for swept source. And the difference being is that swept source gives you an image all through the depth of the eye, from the vitreous, retina, and choroid, all pretty much simultaneously. So some of the main attributes of swept source OCT are that it has a deeper range of imaging. You can see from the vitreous to the choroid, and it's higher speed, and we're going to hear more about that later today, really an attribute for OCT angiography. And it also lets us do wide area scans or big volumes. The Topcon device, the Triton, is shown here, and it's, as you know, it has a very easy user interface, and it's capable of getting images deep throughout the eye. And sometimes you can get some pretty amazing images. There's a method to look at the vitreous that augments the ability to visualize the vitreous. This is my vitreous, and you can see how basically ancient I am because all these bursa are there. And here's a high myope, and you can see that this person really has thickness of the choroid and the sclera about 1/10 of what we would expect to see in that area. But you can go all the way through the eye, and we can see blood vessels behind the eye. So now we can see the vitreous, the retina, choroid, sclera. Soon, back here is going to be brain, right? So the next part of the talk I'm going to talk about is not really specific to how swept source works or whatever, but it's using some information obtained from swept source OCT to look at AMD. And AMD is a hard thing to define. If each of us made a definition of what age-related macular degeneration was, you first of all realize it's kind of hard to do because we really haven't defined it as a specialty or as our field. And the second thing is everybody has a different idea. So this is just one idea. And it starts out with thinking about what a disease is. And a disease, there's a million things that can happen to a person. And you look at those million things and you try to pick out some pattern of those million things into a kind of a construct. And we have an idea about, well, maybe this is a disease and here are the symptoms, here are the signs. And we can go back and look at other patients, see if that applies to them too, and test that construct. And that's how we refine diseases over a long period of time. So this leg here is red, painful, swollen. We say, oh, maybe that leg has inflammation. Well, people really started defining inflammation back more than 2,000 years ago. This is Celsius. Now, we named the temperature scale after Celsius, but Celsius wrote a kind of an encyclopedia about a lot of different things, one of which was disease. And back in those days, they thought inflammation was a disease. And that whole idea about redness, pain, and swelling, that came from him. And that was a kind of a construct at that time. And throughout the ensuing years, people got to be able to test that construct for sensitivity and specificity and the like. Since then, we have 100 different ways of diagnosing inflammation. We have 100 different kinds of inflammation that we've been able to define. Age-related macular degeneration is much different than that, in that it's a relatively recently described disease. People had the idea about cuneous degeneration, that sort of thing, but it really wasn't defined until Gass looked at it in a very systematic way in the 1960s, and he published a paper in 1967. This paper was 139 pages long, and I would recommend that you read it because it's unbelievable. It was published as a supplement to the AJO, and that basically started medical retina. Then he later defined Drusen and saw that Drusen were a risk factor for AMD. But his technology at the time was pretty low tech. So he had a 30-degree fundus camera and he took color pictures with Kodachrome, or he did a fluorescein angiogram with Tri-X film. I'm not even sure you can buy that anymore, but Tri-X film, and he used Ratten filters. So later studies, epidemiologic studies, quantified the risk of Drusen. And soon it became the idea that early AMD was Drusen. And they were kind of synonymous with each other. If you're talking about one people understood, you talked about the other. Remember, Celsius, even 2,000 years ago, had several things that defined inflammation. Now we have one thing that defines early AMD. That's it, Drusen. But you can find Drusen in many other kinds of diseases, not only AMD. We're all familiar with looking at a choroidal nevus, for instance, and seeing Drusen on top of a choroidal nevus, or late onset retinal degeneration, Sorsby's, North Carolina macular dystrophy. All these things have Drusen, so Drusen aren't specific. In 2008, a study was done that showed that there was focal hyperpigmentation was a risk factor for late AMD. So this is more than 40 years after Gass described what AMD was. Somebody came up with a different risk factor. Only one other one. I actually published a paper in 2003 and showed it was a risk factor for type 3 neovascularization. But then people accepted the idea of focal hyperpigmentation was also a risk factor for AMD. So in 2008, the ARIDS group published a paper in which they said that this was the kind of flow diagram of what happened in age-related macular degeneration. You had either many intermediate drusen, one or more large drusen that went to focal hyperpigmentation, from focal hyperpigmentation to geographic atrophy and choroidal neovascularization. But concurrently, and even before that, there were many things that were described that weren't included in that classification system. One of which was pseudodrusen, which were described in 1990, and they were described as pseudodrusen best seen in blue light. Now, at the time the people described that thought they were in the choroid and that they really weren't drusen. And thus, the idea of pseudodrusen, I think, maybe held it back from being an accepted kind of phenomenon, because pseudo kind of complicates an issue for any sort of naming. And many years, people didn't really accept it was a real entity. And later, we found that it was these accumulations of material underneath the retina and called them subretinal drusenoid deposits. Then it wasn't considered to be AMD either. It went from being a pseudo-drusen or fake drusen to being not part of AMD because it was above the RP. But curiously, in between that time, all of the major studies, particularly those involved with the Wisconsin Reading Center, and this includes Beaver Dam and ARIDS, thought they were a special kind of soft drusen, and therefore they were classified as part of AMD. So this is a patient, this picture is relatively small, I just noticed this, but there's some kind of drusen here. They're actually pseudo-drusen, as you can see by those arrows. And this patient, after 7 years, as you'll see, developed an area of geographic atrophy. Now this area of geographic atrophy developed without any focal hyperpigmentation. So this kind of developed a late phase of AMD without going through those steps that were outlined in that 2008 paper. So if you read papers from the ARID study and the like, and they talked about soft drusen, they're really talking about one of three things. They're talking about pseudo-drusen, pseudo-drusen plus regular soft drusen or soft drusen. And we can't take that apart anymore. That was mixed in together, and we can't extricate the pseudo-drusen out of that mix. Polypoidal choroidal vasculopathy was described by our group, but principally by Dr. Larry Yanuzzi, and that was in 1991. And we first saw that in kind of older white ladies. And we thought this was kind of a novelty, and we had fellows from Japan, and they went back to Japan, and they found that 50% of the neovascularization in Japan, and also found in Asia, was really polypoidal. This was not included in that ARIDS classification either. And for many years, I can tell you, people didn't think polypoidal occurred. Type 3 neovascularization was originally described by Emmy Hartnett, and she called it deep retinal anomalous complexes, and then it was called RAP, and then it was finally called type 3 neovascularization. This is a kind of a newer kind of idea of neovascularization where blood vessels grow from the retina down, create a PED, there's telangiectasis of the retinal blood vessels, hemorrhages and leakage into the retina. And initially it's not choroidal neovascularization, right? Because there's no choroidal component to it. And I can tell you for many years people didn't accept that as an entity either. So we can start with this 2008 idea, and we have to add a couple things to it, right? Because it's not exactly right. So if we're gonna add all these extra things, it would look like this. You can start off with soft drusen, but you have to remember, at least in the ARID study, that could mean that you had pseudo-drusen or pseudo-drusen plus soft drusen or soft drusen, and they could go to focal hyperpigmentation, but maybe not, right? I showed you that case with subretinal drusenoid deposits, the pseudo-drusen that didn't have focal hyperpigmentation, and they could go to choroidal neovascularization, but type 3 isn't choroidal neovascularization. And finally, geographic atrophy is kind of an unusual entity. We're undergoing a lot of revision of the naming of that. But Shirley Sarks and John Sarks showed that 45% of the cases of geographic atrophy actually have undetected C&V in histopathology. So geographic atrophy, it's not an either or thing. It's kind of a mix of those, both of those things. I just want to take a step back and talk about drusen and pseudo-drusen, or subretinal drusenoid deposits. Drusen, or lipoprotein accumulations underneath the RP in the inner portion of Brooks membrane. Now, that has the predominant lipid in drusen is cholesterol esters. Subretinal drusenoid deposits are very similar appearing kind of material that's also made out of lipoprotein particles on top of the RP. Now, the interesting thing is that drusen are found commonly where cones are found, and pseudo-drusen are found predominantly in areas where there's rods. But in either case, it gives you the idea that there's a hard time processing the lipids involved from these photoreceptors, or at least somehow related to these photoreceptors, leading to the accumulation of this material either above or below the RP. So if we kind of accept the idea that that's an aging-related thing, there's a build of extracellular material, we can say that really both are associated with aging and part of the AMD spectrum. Then if you do that, many things fall into place. There's a new way, I think, to classify AMD, and that's to consider that the accumulation of extracellular material is really the hallmark of early AMD. And we can either have drusen with or without focal hyperpigmentation, or we can have these subretinal drusenoid deposits, which are the pseudodrusen. Late AMD would be the development of atrophy or macular neovascular disease. I think macular neovascular disease is a better term than choroidal neovascularization because type 3 neovascularization really isn't choroidal to begin with. But it's all in the macula, and that's really the important part, that we have neovascularization in the macula, which is really like a kind of a bad thing. And what's more is all of this stuff is influenced by how thick the choroid is. Here's a patient with soft drusen, and you can see that they're relatively large, round kind of things, blobs, and towards the center of the macula they get confluent, and as you go away from the center of the macula they get smaller. Notice that the choroid is relatively, you can see the choroid, and you can see some of the larger blood vessels inside the choroid. There's some focal hyperpigmentation in this patient as well. And note that the choroid is kind of average thickness. This is that drawing I made in 2003 that shows that I thought focal hyperpigmentation was that the RP cells detached and came in the outer retina. RP cells can make VEGF to make C and V, but they can also, if they made VEGF here, would recruit retinal blood vessels to grow down across that VEGF gradient. These are pseudodrusen, and you can see these pseudodrusen are a little bit whiter than typical drusen. And notice that you see the choroidal markings quite well, and some of the choroidal blood vessels are really almost yellow. And that's a kind of a thing that you see in patients who have very thin choroids. This patient is relatively thin choroid, as you can see here. You can get combinations. Some patients have soft drusen in the middle and have pseudodrusen where the rods are. And you can see there's kind of intermediate sort of thickness of choroid. So, we did a number of studies and found that subretinal drusenoid deposits are associated with thin choroids and the other way around. And the converse of that would be soft drusen are associated with normal thickness choroid. We also wrote a paper about people who have really thin choroids. Now, you can get really thin choroid just through aging, but the natural person to get a really thin choroid is a high myope. See? So when a high myope gets older, their choroid gets extremely thin, and guess what? They don't have drusen or pseudodrusen. That's an unusual thing to think about, since myopia is not correlated in any way with complement factor H or ARMS 2. So conceivably, they have the same kind of genetic makeup, but they don't go on to show any signs of early AMD. So I showed you about very thin, normal. What about thick choroids? I noticed a while ago that there is a kind of a special drusen associated with thick choroids. And I'll show you some of the characteristics. I made this drawing to just show that. This is supposed to show regular drusen, and you notice they have a poorly defined outer border. They're kind of blob-like, and I didn't show them confluent here, but they're kind of pushed together. And I drew the idea that you could see the larger choroidal blood vessels underneath. And this patient, this eye also has focal hyperpigmentation. These newer kind of drusen have strange shapes. They're well-defined. You can see how these are kind of cut out sort of shapes or undermined edges or whatever. And notice that the choroid is kind of, it's hard to see any blood vessels in the choroid. It's red. Now there can be some focal or changes in pigmentation or regional variations in pigmentation, but it looks different than the regular choroid. So since these are associated with thick choroid or pachychoroid, we call them pachychoroid associated drusen. That's too much to say, so I just changed it to Pachydrusen. Okay, so these are Pachydrusen kind of variants. And here would be a patient with Pachydrusen. Here's some of that pigmentation in the open arrowhead. Solitary big druse. Notice when you usually have, say, large drusen from regular soft drusen, if you have a big drusen here, a big druse here, you'd have many smaller ones around this. But curiously enough, with this Pachydrusen sort of idea, that they can have a big druse all by itself, and you can see how thick the choroid was, almost 600 microns thick. Here's another patient with Pachydrusen showing some other characteristics. Instead of being localized in the center part of the macula, they're distributed around. They're not confluent, and they have funny shapes. If you look at them, they're kind of unusual. Here's an autofluorescent picture showing that there is some RP changes. ICG angiography shows multifocal areas of choroidal vascular hyperpermeability, and the OCT, very thick choroid. This is an African-American woman, and she has these Pachydrusen around the nerve, and her choroid also is thick. So to study this in greater detail, I looked at 94 eyes of 71 patients and looked at a number of different features about them. and excluded some of the stuff that you would usually expect to see, and I also made sure that they didn't have a history of central serous. And you can see their median age was relatively old, like we'd expect to see in people with Drusen. Their subfoveal choroidal thickness had about a 12-to-1 ratio from being thin to being quite thick. Soft Drusen were found in 45 eyes, and that was the predominant type of Drusen that was found. Subretinal drusenoid deposits with or without Drusen, next most common. And this newer kind of Drusen, this Pachydrusen in 11, which is almost 12%. You can look at the choroidal thickness of these. These are regular Drusen. These are the pseudo-Drusen or subretinal drusenoid deposit types. And these Pachydrusen patients, just identifying them based on what the Drusen looked like, you can see their choroid was much thicker than all the others. If we look at the choroidal, the cumulative distribution of these things, and it might be a little bit hard to see, but green shows these Pachydrusen, it's really in the spectrum of things. It's not that there's something completely different. It's that soft Drusen are found, say, up through here, then we start seeing more and more Pachydrusen patients among the mix. So it isn't so much a sharp cutoff as really kind of a gradient of probabilities, that the thicker it is, the more likely you are to have a thick choroid. So just to summarize some of the difference between soft Drusen and these Pachydrusen, the soft Drusen aggregate in the central macula. They're round or oval and they have a poorly defined border. Pachydrusen are scattered throughout the macula. They don't show any aggregation. They can have ovoid or complex shapes and they're fairly well defined. The regular soft Drusen decline in size as you get away from the center part of the macula. There's no radial relationship here. Soft Drusen can become confluent. Pachydrusen not so much. And soft Drusen can have pigmentation on their surface. There's no pigmentation for these Pachydrusen. If you see a big soft Drus, usually in the area, there's going to be some smaller ones. Pachydrus, not so much, right? They're just sitting there isolated by themselves. And the background choroid, you see choroidal blood vessels, soft Drusen. Pachydrusen, you don't usually see that. You got that stuff? Yes? I just want to mention one thing, is that Drusen, before people you say, well, you can't tell soft or large. I mean, you can't tell soft or hard. That's hard to quantify, so soft Drusen are big and hard Drusen are small, so we'll just say large or small. But if you say that, then you're going to ignore the shape, the contour, aggregation, and topographical distribution of Drusen, so large and small is a kind of a dumb way to classify Drusen, in my opinion. So, you guys are now smart, I think. I'm not sure. But now is the time for a test, okay? So I'm going to show you the stuff here, and you have to tell me whether it's soft Drusen, pseudo-Drusen, Pachydrusen. And because you know that, you have to tell me how thick the choroid is, whether it's thin, moderate, or thick, just by looking at that picture. You don't need OCT anymore, you have swept source brain. So what are those things? Soft Drusen. How thick is the choroid? Moderate. So you're correct. How about these? Soft, pseudo, or Pachy, and is the choroid thin, moderate, or thick? Soft and moderate. The only difference was that this patient has focal hyperpigmentation. It's a little bit more advanced case than the one I showed you before, moderate thickness and choroid. Notice that the choroid, you can see the markings very well. The vessels are starting to turn yellow, especially up here. Reticular pseudo-Drusen. Who uses that term? Yes, and is the choroid thin, thick, or in between? Thin. And that's true. Look at how thick that choroid is. 38 microns. It's kind of hard to believe, right? What kind is that? Is that soft? Pachydrusen. And how thick is the choroid? Thick. That's right, 352 microns. So now you know all those differences. Now here's a kind of curious thing. If we had patients with, say, pseudo-Drusen, and we look at their risk alleles, guess what? They're not any different than regular AMD. So if I told you someone's risk alleles, or I said they had the risk alleles that were, put them at risk for AMD, what do they have? You couldn't tell me if they had pseudo-Drusen or soft Drusen unless I told you how thick their choroid was. If I told you their choroid was 43 microns, you would say, oh, they have pseudodrusen. If I told you it was 243 microns, you would say, oh, probably have soft drusen. Right? So knowing the choroid tells us kind of what the AMD is going to manifest itself as. So to be able to classify or be able to understand the early manifestations of AMD, say, you need to have an OCT that lets you look how thick the choroid is. That's where kind of, at least where swept source, that's kind of an advantage, I think, for that kind of imaging modality. And we know that the soft drusen, or I mean, the subretinal drusenoid deposits are associated with GA and CNV in many studies. And there's probably more data about that than there is about focal hyperpigmentation being associated anyway. So we did studies looking at polypoidal, the genetic sort of variants in that, and there maybe some studies show a little difference with AMD, but other studies don't. And we reviewed this in an article actually, and pretty much patients with polypoidal have very similar risk alleles in any kind of specified population as regular AMD patients do. Curiously, patients with polypoidal have thick choroids and patients with regular CNV don't. So here again, it's something that if I told you some of these risk alleles, you wouldn't really be able to tell me so much whether they had polypoidal versus AMD unless I told you how thick their choroid was and also maybe what their race was, right? You need to know other things to know that what's going to come next. We look at patients in, at least in the United States, this just came out, looking at people with pachychoroid with choroidal neovascularization, and they have exactly the same risk alleles that patients with AMD do, right? So even though kind of started with the idea that maybe pachychoroid, this thick choroid with choroidal neovascularization was somehow a different disease, the risk alleles are the same as for AMD. So if I told you someone's risk alleles, you couldn't tell me if they had pachychoroid, which typically gets either polypoidal or type 1 CNV, versus anything else in AMD, unless I told you how thick the choroid was. If the choroid was, again, 243 microns, you would say, oh, those are soft drusen. If I told you there were 543, you would say, oh, probably had Pachydrusen, or at least probably polypoidal or type 1 CNV. You'd be more willing to bet on that. So polypoidal and type 1 are associated with thick choroids, as I said, and these Pachydrusen are associated with thick choroids. We're still working on these kind of correlations. So I showed you a little bit about how disease manifestation in AMD depends on how thick the choroid is, and that this could form a basis of how you classify AMD. Because older classification systems use color photography by and large, and we can go back now to what we know from looking at patients and say, I can guess they had a thick choroid or not, but really in a classification system, you'd like to have the thickness of the choroid. Patients with thin choroids, generally speaking, get pseudodrusen or subretinal drusenoid deposits. People with moderate thickness choroids, the soft drusen, thick choroids, Pachydrusen. And the future manifestations of AMD are kind of related to that as well. This looks complicated. This is a derivation of that 2008 idea, but if you read through it kind of slowly, you can see it kind of all makes sense. If we start with subretinal drusenoid deposits, which are the pseudodrusen kind of thing, they can regress and get outer retinal atrophy. I didn't really cover that much in this talk just because of time, or they can go to geographic atrophy. Subretinal drusenoid deposits, though, often can go to macular neovascularization, particularly type 2 or type 3. I should say macular, not choroidal. People with pseudo-Pachydrusen with a thick choroid may be more likely to go on to have polypoidal or to have type 1 neovascularization. Soft drusen can regress to form geographic atrophy or can go to form neovascularization, and if they did, that would usually be type 1. Once they get focal hyperpigmentation, they can get type 2 or 3 as well. So older classification systems are based on color photography. The present system relies on OCT predominantly. I'm not sure we even need to have any color photographs anymore. With the speed of being able to get volume scans relatively rapidly, being able to slice through that data, we can tell on an unfast way what kind of drusen are present just by their physical characteristics. And then we can also look at their choroid, and by putting those two together, we can end up with a classification system that lets us predict the future to a certain extent, which the other older classifications couldn't do. But by and large, it still is dependent on the ability to see the choroid, at least in terms of thickness. And I think you realize that this classification system then would pretty much meld into what's coming next, which is really to integrate OCT angiography. So I'd like to thank you for having the ability to give this lecture. It's certainly an honor, and I'm glad that y'all came to this first sort of inaugural meeting on Source OCT.